Okay, so here we go. Good morning, everybody. I thought I spend a minute introducing Andrew just because he joined PNNL recently, last November, but I know many of you know Andrew or know of Andrew already. So Andrew is a senior scientist. He came to PNNL, as I said, in November after a successful career at NCAR. His interests are in global climate model development and analysis, especially from the point of view of cloud processes, parameterization. Andrew has an impressive resume with many papers, many leadership roles, grants, teaching, visiting positions in Europe and New Zealand. I just want to add two intriguing things. I think his last paper is actually about rainbows in climate models. And he's also, he has authored a paper, a book called Demystifying Climate Models. So today, Andrew is going to talk about perturbed parameter ensembles. And Andrew, I leave it to you now, and I'll disappear.
Okay, great.
Thank you.
Let me share my screen. Thanks, Claudia. Thanks for the invitation to be here. It's been a really fun ride so far at PNNL and in the DOE ecosystem, and I'm getting more spun up on E3SM. It's all project driven, so where I fit into all these projects is still evolving. But it's good to see so many familiar names, if not faces, so that's great. And what I'm going to do, as Claudia said, is talk a little bit about some of the work we've been doing in CESM, which is parallel to the things I know are happening in E3SM on perturbed parameter ensembles, and in particular, talking about the interactions of forcing feedback and parameter uncertainty. This is work that I've done with collaborators at NCAR, so Margaret Duffy, Trude Idahammer, Hugh Morrison, who I saw on the line, Kate Thayer-Calder, and then at NASA, Greg Elsasser and Marcus Van der Wakke. I think I saw Marcus on the line too, and Duncan Watson-Paris, who's now at the University of San Diego. So there we go. So sort of the science motivation before I talk about sort of a perturbed parameter ensemble is, are aerosol forcing and cloud feedback actually related? And this has been sort of, people have thought about this in a high level context of, oh, well, if you have a high climate sensitivity driven by cloud feedback, does that mean you have to have a high aerosol forcing? So I really want to look at this at the process level. And looking at cloud feedbacks and climate sensitivity in both aerosol forcing, I'll give a 2-second introduction. Well, 2-minute introduction just to get everybody on the same page, but I'm sure most of this group actually knows more about it than I do. I'll talk a lot about the methodology, the perturbed parameter ensemble, and I'll show some results, some general results from emulators, some aerosol forcing and cloud feedback results, some preliminary results into interactions. This is still in process. That you can see the work's about 2/3 baked. It still needs a little bit more before it becomes an actual paper. So general climate forcing aerosols, in particular aerosol cloud interactions. So aerosols are places where cloud drops nucleate, and that actually then changes cloud drop numbers with all kinds of knock-on effects on clouds. That aerosol cloud interaction is the largest uncertainty in the anthropogenic radiative forcing of climate. This is from the last IPCC report. So this is actually quite important because basically aerosols have modified the radiative effects of clouds over the historical period by potentially about a watt. And that makes it hard to actually use the historical period to actually understand the future because the aerosols are changing at the same time the climate is changing. And I know this has been an ongoing pain point in E3SM. Based on the magnitude of this, it tends to be very large in models when we go at it as a process basis, and E3SM is no exception. But I understand, and some work that I saw from Xiao Cheng, that E3SM v3 is making remarkable strides in this. And that's a really interesting discussion also. So from a climate perspective, what clouds do is they're basically two things, and this sort of illustrates it. Clouds are white, which means they reflect radiation back to space. That's in the short wave. It's a lot. It's almost 50 watts per meter squared. And clouds are cold, and that means they act like a greenhouse effect. That's the long wave on the bottom. And that's also fairly large, but not quite as large. So the net is a large cooling effect. And that large cooling effect of 20 watts per meter squared of cooling. If you go back to that anthropogenic radiative forcing and you think about doubling CO2, that's about 4 watts. So changes to clouds in response to changes in climate, what we call a cloud feedback, small perturbations in clouds can exert a pretty large feedback on climate. So some work from Mark Zelenka, which basically shows looking at climate feedbacks in the CMIP6 models. And what it shows is that all of the uncertainty in the climate feedback. So the first one's the Planck feedback, that's sigma t to the fourth. It's a large negative feedback. You take a black body, you warm it up, it radiates more to space, it cools itself down, it stabilizes it. That's a good thing, prevents a runaway temperature. You don't want to have an overall positive net feedback. We would have a runaway climate. So you want it to be negative, but there's these other positive feedbacks that push against it, chiefly the water vapor, albedo, and cloud feedback, and all the uncertainty is in the cloud feedback. That uncertainty in the shortwave and long wave, you can see in particular for CMIP6, there's some high shortwave cloud feedback models. Those are the ones that end up, you can see on the left here, with a high equilibrium climate sensitivity, or ECS. And so understanding the cloud feedback is actually critical, and the uncertainty in the cloud feedback. And this is a large spread in cloud feedback across models. And I'll show that we can actually duplicate that just with parameters inside of a model like CESM in the cloud. So that's actually also very interesting. So let's talk about this perturbed parameter ensemble that we did. So this is not the first time somebody's done this. This may be fairly comprehensive. We've been using some new methodologies to do this. We're using CAM 6.3, that's the CMIP6 model. It's somewhere around E3SM version 1, version 2, and its physical parameterizations. We modified 43 parameters across the turbulence, microphysics, deep convection, and aerosol and activation schemes. We made all these parameters nameless for the connoisseurs of E3SM. You may notice a lot of things that are also in E3SM, in club, in the MG microphysics, and in the ZM convection there, and in some of the MAM or the aerosol activation. We ended up with 263 parameter sets, 262 plus the default, and we selected these using Latin hypercube sampling, which I'll explain in a minute. And we built a methodology to actually be able to run these efficiently and also make it extensible, which I'll describe now. So this was a nice exercise in how to actually build something that's robust. This would work quite well, I think, in E3SM. It uses underlying a lot of the same sort of general seam commands to build, compile, run, configure the model. We put it all into a single Python script that can actually launch all these things. So we have a couple of Python scripts. One is an offline notebook for Latin hypercube sampling of parameters. So we can set parameters, ranges, and the number of ensembles we want. This generates a file using Latin hypercube sampling of a set of parameter sets with names of ensemble members, typically just numerical. We then can take a Python script. It's a single shell script with all the seam commands in it. It builds and clones a control case, the default, and then it clones it for each parameter set, and it goes to that file and then drops all these parameter sets in there in the name list. It changes the name list for each of these, and then it launches all the simulations. We can typically do on a batch queuing system on a moderately sized supercomputer, meaning something in the NSF Wyoming data center, which is much smaller than many of the DOE machines. We can typically run 50 of these things at once, and they're done in a day. I mean, your mileage may vary with the use of a machine in a queuing system, but it runs pretty fast. It's a great way to blow computer time. It's a stupidly parallel operation. But the neat part is it's fairly simple and it's extensible. We actually had an error in one of our parameter ranges. We extended it and were able, as I'll describe, to add 12 parameter sets, didn't have to throw the whole thing out to get back to where we wanted to be statistically. And I would also note that it's very traceable. So we have a file that describes exactly what parameters are in each simulation that is keyed to the case name, so it's easy to trace. We also have all the, you don't have to dive into all the cases to figure out exactly what you did. It's all very in the open, and it's very easy to actually access and analyze in this context. The Latin hypercube sampling, many of you are familiar with, it basically samples in a multivariate space. I'm showing 3 dimensions of the 43 dimensions, which would explode my head to try to figure out how to describe or display that. But the darker things are closer to the origin. What it does is you'll notice that is basically a shotgun and distributes everything. The whole point is to distribute these in parameter space. So if you look at the PDF of any parameter across its range, it's flat. It's equal frequency in all of these things. And the distance from all these points, we try to actually to maximize that distance to fill out the parameter space as much as possible. So what's the interesting thing about this is it can be extended. You can keep running extensions to it, and people are doing it now. You can run any configuration with CESM. So for example, Daniel McCoy has run 263 parameter sets for nudge experiment field cases. I'll show what we've done, but he's done separate ones. We've also done it with the single column model with SCAM. There's a PPE that exists, which I think Marcus is working on. And then we also extended this. So we started with 250 parameter sets, 250 cases plus the default case. And then we found out we actually had one parameter where it was mostly on the edge of its range. We wanted to extend that range to make it more realistic for what we thought was reasonable. So what we did is we went back and found the average Euclidean distance between parameters. So it's basically a distance metric that calculates from each point the distance to all the other points in 43 dimensions, comes up with a number for that, 260 some odd numbers, averaged over all the parameters for each of those, 43. So you get an average Euclidean distance averaged over 43 parameters for each of those. And we came out, that's what you're seeing now for the first 250. We then ran another 7,500 parameter sets with the extended range, and we picked 12 with the Euclidean distance greater than this average across those, and with parameters in the new range. And that gave us 263. And statistically, it gives us the same spacing in this new parameter range as we had for the others. So then what we wanted to do is explore the forcing and feedback. So what we did is we did three types of simulations, 3 years each. We used the root mean square error to figure out exactly how many years we needed to run for this application. We looked at 10, 3, and 5, and I know there's some discrepancy about what people want to do, but we decided to try it with 3 years. It seemed to produce reasonable results. They're all fixed SSTs, so climatological AMIP. We did present day, straight up sort of AMIP simulation with specified SSTs. We then did one with the same SSTs, but pre-industrial aerosol emissions. I mean, again, this is 3 years, 263 simulations for each of these. And then we did a third set with present day SSTs plus 4K and present day aerosol emissions. All this data is available. It's been published. There's a DOI for it, and there is a paper that is going to be submitted by Trude Idahomer soon documenting all this. Some of these figures are from there. And so what you get is, if you look at the top of the atmosphere residual on the right, which is kind of interesting, the default case is shown as the dashed line, the vertical line. So the default is a couple, for the present day, is a couple watts positive when we run an AMIP, a climatological AMIP. And then those are the PDFs. You can actually get very, very large top of the atmosphere imbalances. You can maintain this stably for 3 years or longer because it's a fixed SST. So there's an infinite flux of heat at the surface that enables you to keep it stable. And you can see on the left, the CCN are lower in the green, which is the pre-industrial simulation because it uses pre-industrial aerosols. So just some spread across the PPE for these different sets again. If you look on the upper left, you see there's quite a large range in the overall ice water path, and the lower left, there's a big range in the liquid water path. It doesn't go negative. That's actually just a standard deviation. And you'll notice also the dashed lines, which are the default, are not the median. There's no reason why they need to be the median of the PPE. In some cases, they're outliers, which is very interesting also. And then, so you see quite a big spread in liquid water path, which is what's contributing to these large changes, and ice water path, which is contributing to the top of the atmosphere differences. You can also then difference these two sets. So if you difference the present minus pre-industrial, you get the aerosol forcing. If you difference the SST4K minus present, you get essentially the feedback. So this is, so for example, if you look at the shortwave cloud radiative forcing, the blue is the forcing, and so basically that's the spread of the total indirect effect for indirect effective clouds, and then the feedbacks are essentially the right, or the orange part on the right of this plot. And you can see also we get increases in cloud drop number when we use present day aerosols, we get big increases in cloud depth and burn there. If you look at the total shortwave cloud, the total shortwave radiative effect, which is really the forcing, that's on the lower right, direct and indirect. And you can see for the forcing, it's actually very peaked, which is interesting. It's actually a pretty tight range, which is something interesting in and of itself. We can also emulate this. So this is using a Gaussian process emulator this is the ESEM climate bench emulator from Duncan, which was developed at the University of Oxford. Duncan's now at UCSD. And what we're doing is actually emulating the pattern of long wave cloud forcing and using test and training data. And you can actually see we can do a really good job at doing this. And the RMS averaged over 50 training samples is about 1 watt per meter squared. There's some anomalies in different places, but it actually does a pretty decent job of emulating patterns in things with these Gaussian process emulators. We can also look at sort of parameter sweep experiments. So there's what we're showing here is using a different emulator that emulates the global mean, that's in gray, and then the samples are actually in purple. And what we're doing is showing global average, say, top of the atmosphere flux as a function of 2 parameters. One is the autoconversion exponent in the microphysics, which actually, as you change that, you control how fast the rain falls out of the model. And so you control the overall liquid water path. So the top of the atmosphere flux is sensitive to that. And the bottom is the ice fall speed factor. So that really controls the mass of ice in the atmosphere. And you can see it affects the shortwave or the total, and then restom and residual top of the atmosphere flux, and then the shortwave and long wave cloud forcing. So in particular, the ice fall speed factor, lower right, is tightly correlated with the long wave cloud forcing, which is not surprising because it's mostly governed by the ice mass in the atmosphere. We also can come up with slopes to that to look at the sort of relative importance of parameters by actually individual by individual field, and that's this plot. So these are normalized slopes now. And I think, yeah, these are normalized also over the parameter range to sort of make sure we're equating everything equally. So the horizontal axis is a series of output fields. You can kind of read them from the top of the atmosphere. Restom is what I showed. The cloud forcing's in here. The last one on the right of each of these is the sulfate burden. And what this shows is the relative slope. So the darker the color, the stronger this slope and the stronger this slope here, basically. And so each of these plots is one of these little boxes in the global, and we also can do it regionally. So what you can see, and these are by parameter, so you can see which parameters are governing which fields in the model, essentially, what the sensitivity. So here's the autoconversion exponent, here's the ice fall speed. You can see those light up, particularly in the tropics for the ice fall speed. And then interesting, so for example, this thing at the bottom, which is pretty strong for precipitation, is the buoyancy change in the deep convective parameterization. So you can actually go and look at this. Can be used for tuning. We're actually using this sort of thing for tuning the model. Last, I want to talk a little bit about last 10 minutes or so about forcing and feedback. So our aerosol forcing and cloud feedback related. We're going to use the PPE to look at that. What are the key interactions and processes? And I may skip some, well, I'll mention the earlier work, and then we're going to look at these questions in the PPE. The first thing to recognize is there is an aerosol mediated cloud feedback. Not all cloud feedbacks come through temperature. Some of them come through climate changes that affect aerosols. And if your model doesn't have aerosol cloud interactions, it doesn't have that component of the feedback. So this contributes to the spread in the CMIP6 ensemble. What this shows is it shows a couple sets of coupled simulations. The 2 that are red and black are 2 different RCPs, 8.5 for red, 4.5 for black, and they have the standard decreasing aerosol in the 21st century. The blue is redoing the red one with RCP 8.5, but keeping aerosols at like 2010 levels, so high aerosols. And what you can see is if you analyze the feedback using differences between the beginning and end of the century, you get a very different answer with the same model code, because this includes the difference in aerosols. So these are kernel adjusted cloud feedbacks where we've taken out the effects of other things. So we also built an aerosol kernel. This was done in a quick way, but it works. And so we take out the aerosol effects based on the change in AOD in an integrated way in these models. When you do that, you get something that looks like this. So now this harmonizes things a lot more, and it gets higher. The feedbacks are actually higher. The total difference between the decreasing and fixed aerosol cloud feedbacks is pretty large. And we totally remove any difference in the Northern Hemisphere because all that difference was due to aerosols. What's interesting in the Southern Hemisphere is you do see differences, and those differences are actually due to differences in climate between the decreasing or between the different simulations. So we have the same aerosol emissions, but you get in the Southern Ocean, but you get a change in wind speed with a higher warming case. That gives you a change in sea salt, and that gives you a change in CCN, which gives you a change in shortwave cloud forcing, which is interpreted as a cloud feedback in this context, and it's an aerosol mediated cloud feedback. It's not due to temperature. It's due to changes in emissions due to aerosol. So that has to actually be considered. So let's go back to the PPE and look at how the ACI, so going back to the forcing, depends on the mean state. So this is the ACI across all the different simulations, 263 dots here. And what's shown is this as a function of the mean state for three fields, the total cloud fraction, the CCN, and the shortwave cloud radiative effect. So what you can do is say, okay, well, the shortwave cloud radiative effect, we know that number. It's about 47 plus or minus 3 watts per meter squared. So if you go to this bottom plot, the only credible simulations would be in a narrow range, but they still give an ACI of somewhere between -1 and -3. It doesn't actually help us that much for a constraint. There's some also constraints on CCN, and there's a constraint on the total cloud fraction. You do see stronger negative ACI with a larger cloud fraction, lower CCN, and larger negative shortwave cloud effect. The mean state actually seems a little bit limiting, not totally, but I think some of this has to do with susceptibility, that the marginal clouds, as you get to parameters that encourage cloud formation, those marginal clouds tend to be more susceptible, so you get higher aerosol cloud interactions. You can also then sort of do the same thing we did before and look at slopes, where these are the differences now, the deltas between pre-industrial or between present and pre-industrial, and you can see what affects the delta. And it's essentially precipitation, so the autoconversion and accretion are important for governing ACI, the stratiform ice and liquid activation, including some of the subgrid vertical velocity terms for the activation and the ice fall speed, and then the horizontal variance, vertical velocity skewness, and the LWP variance in the turbulent scheme are also kind of important. Those are these club parameters over here. But we're still diving more into this. There's a lot of information in here, but it's quite interesting and rich in what you can find. Last thing I wanted to do is comment on cloud feedback. So the green is the spread in the cloud feedbacks from the CMIP6 ensemble. So it's similar to what I showed you on Mark Zelinka's plot at the beginning for the total, the cloud, the shortwave, and longwave feedbacks. The purple is the PPE. It's basically about the same range. We can do that with just parameters. And so this is looking at the same sorts of plots for aerosols, where now we've put essentially the total, an estimate of basically the total cloud, the total chain, these quantities, or the cloud feedback chain in between between the SST4K and the pre-industrial, and then we have the actual present day value. So present day value of cloud fraction, ice water path, and shortwave cloud radiative effect, and you can see the same thing. There's a stronger positive cloud feedback, essentially this change in the the vertical is the shortwave cloud feedback with or the shortwave and longwave cloud feedback with a larger cloud fraction because there's more cloud to lose, with a larger negative shortwave cloud radiative effect, and with a higher ice water path, interestingly enough. And I think some of these susceptibility things are pretty much the same. Again, you can look at these feedback relationships. They're different than for aerosols. The deep convection, increasing ice increases the long wave feedback. Microphysics, the ice fall speed, autoconversion change, and ice mass are important for the long wave, and the subgrid nucleation for ice, subgrid vertical velocity changes the total cloudiness, but there's not much feedback effect. And there's some important turbulence of parameters in club that also have an impact. Lastly, you can correlate these things in space, and you can correlate the cloud feedback and the aerosol forcing. And interestingly enough, they do seem to be negatively correlated spatially. Stronger positive cloud feedbacks, stronger negative aerosol cloud interactions as a function of space. The southern hemisphere, there's not much forcing, so it's not very significant. So we're starting to dive into this a little more. But again, I think this has to do with susceptibility as you push for more and more cloudiness, or you have a lot of thinner clouds, they tend to be actually more susceptible to both these things. And we're sort of looking at why right now. So the aerosol mediated cloud feedbacks exist in complex GCMs. These need to be analyzed. This causes spread across models due to the aerosol diversity. The aerosol forcing seems limited. It's stronger with thicker base state clouds. This matches parameters that control liquid water path and number processes. And cloud feedbacks are larger with thicker clouds. There's more ice and a higher cloud fraction. Ice processes and accretion are critical. So one of the advantages of parameters is parameters affect specific processes. It's not just twiddling knobs. Those knobs are focusing on particular processes. If you twiddle a knob and the process isn't important, nothing's going to happen to these deltas, for example, even if it happens to the mean state. So that's why even if these states tend to get way out of balance or not realistic climates, I think this actually has quite a bit of statistical power to tell us where the sensitivities lie. And microphysics is important for cloud feedbacks. The number of concentrations and precipitation formation processes are key. It's not just the mean radiative effect. So again, and there are also significant correlations between ACI and cloud feedbacks. Larger ACI is associated with stronger positive cloud feedbacks, and stronger cloud forcing, higher pre-industrial drop number results in stronger ACI and cloud feedback. And so, and the lower drop numbers and sulfate burdens are more sensitive. And I think I will stop there. Yep, that's it. So thank you.